Hello everybody and welcome to yet another science experiment with Mr. Foster. This time what we're going to be looking at is electromagnetic induction and one of the applications of it. To do this experiment we have a strong horseshoe magnet. The poles are at the top here, so we have a strong magnetic field flowing between these two poles. We're going to need a piece of metal foil. This is just simply aluminium baking foil. Nothing special there, I've just folded it in half to give it a bit more strength. We've got two crocodile clips which are attached to leads, and this here is a signal generator. This signal generator creates an oscillating current and you can control the frequency of the oscillations. So there are two dials on it. At top here, this increases the scale by 10 times. So if I were to start with the lowest setting, each of these numbers on the dial are increasing by 0.1 hertz. The next setting up, it goes up times 1. So these would then equate to 1, 2, 3, 4, 5. The next setting up, it goes up to times 10, 10, 20, 30, 40, and so on, all the way up to 10,000s, 10,000, 20,000, 30,000. So this can be used to control what frequency the current oscillates at. We also have an amplitude dial here. We can increase the size of the current. First thing I need to do is set it all up. I'm going to place my magnet in the middle and we're going to clip our foil between the two crocodile clips. This will connect it up to the circuit, and when I turn it on, it will enable current to flow through the foil. So now that we have it all set up, I'll just let you see what happens when the current flows through that piece of foil. You can see at the moment it's laying down, but if I turn the dial up, you'll see it jumps up and down and up and down. At the moment it's set to a very low frequency. You can see it oscillates very slowly, but what we can do is change the rate of oscillations. So it's now oscillating at about 1.1 hertz. The current is flowing backwards and forwards. When the current flows forwards, the wire jumps upwards. When it flows backwards, the foil jumps downwards. So when the current flows forwards through the foil, it induces motion. If the field is pointing away from us in that direction and the current is moving this way through the wire in that direction, we can see that the thumb is pointing upwards and the foil jumps upwards. Now this is known as Fleming's left-hand rule. When the current flows in the opposite direction, in that direction, the field is still pointing away from us. You see now my thumb points down, and that causes the foil to be forced downwards. And this is Fleming's left-hand rule. It shows you in which direction current carrying wire will move when it's placed in a magnetic field. So what we're going to do now is see how this is actually useful. Believe it or not, you use this probably every day of your life. I'm just going to put a bit more tension on this piece of foil, and we're going to increase the frequency of those oscillations. You can hear it's getting a bit noisy, but what happens when we make it have a much higher frequency? And let's turn it up. It's moving so quickly we can't see the vibrations. However, those vibrations at that high frequency are causing vibrations in the air. The air particles around the piece of foil are vibrating as well, and they send pressure waves to our ears, causing this tone. And we can change the tone, the pitch, by changing the frequency of the current. If the current oscillates faster, we get higher pitch sound, because higher pitch sounds are caused by frequent oscillations in the air particles. We can make that incredibly high pitched if we turn the frequency up even higher. Now this is how speakers work. A speaker is basically what we call a diaphragm, which is a thin membrane, attached to a coil of wire in a magnetic field. And when a current, which is alternating, passes through the wire coil is attracted and repelled, just like this piece of foil, and it begins to vibrate. And it will vibrate at the frequency of the current. This causes the diaphragm to vibrate as well, which will cause air particles next to the diaphragm to compress and rarefact. And that's where the particles come together and push apart. That creates pressure waves in the air, which then travel to your ear and let you hear. So that's how a speaker works. I do hope you've enjoyed the demonstration. Please tune in again next time for more science with Mr. Foster.